It is precisely 1 minute past the hour, and we will start. So welcome to the Spectral Geometry in the Cloud seminar. Today we have the pleasure of having Samuel Lin from University of Oklahoma, who will speak about spectral multiplicity and nodal domains of torus-invariant metrics. The floor is yours.
Thank you very much for the introduction. And first, I'd like to thank the organizers for the invitation. Today, my presentation will be based on this paper with the same title, and it's about to appear in IMRN. And this is a project joined with Dan Cianci, Chris Judge at Indiana, and Craig Sutton at Dartmouth College. So today, I will let MG be a smooth closed Riemannian manifold. I should say that there is a version of this for manifolds with different boundary conditions. But today I will focus on the case for closed Riemannian manifolds. In this talk, we let Laplace operator to be minus divergence of gradient. And because our manifold is compact with no boundary, the Laplace spectrum is discrete. So we have the following form of the spectrum. 0 is the first zeroth eigenvalue. This is less than lambda1, less than or equal to lambda2, and so on. And the multiplicity of an eigenvalue lambda, like the matrix case, is defined as the dimension of the corresponding eigenspace. Now, I'd like to mention this classical result of Uhlenbeck, which says the following. So suppose that you again have a closed manifold of dimension n greater than or equal to 2. And now we let ML be the space of CL Riemannian metrics with L greater than or equal to the dimension of the manifold. ML has a natural norm, the CL norm, and therefore it comes with a very natural topology, the CL topology. Uhlenbeck's theorem says there exists a residual set of metrics, RL, in here, such that for each metric in RL, the following two conditions hold. One, the spectrum is simple. In other words, each eigenspace is real one-dimensional. And furthermore, 0 is a regular value for each real eigenfunction. In particular, the nodal sets of these eigenfunctions are smooth hypersurfaces. Let's recall that residual, what's a residual set? It's a countable intersection of open dense subsets. Another way of saying this is that its complement is meager. Okay. So note that each statement here, statement 1 and 2, is not true for all metrics. It's only true for a residual set of metric. So what will be a simple example? So let's say we take T2 to be a flat torus, right? To be precise, a square torus, okay? And suppose that each side has length 1. And let's use x for a coordinate for the horizontal axis and y for the vertical axis. So we know that cosine of k pi 2k pi x are eigenfunctions of the torus. So are sine of 2k pi x, right? And sine and cosine are independent, so we know that the eigenspace is at least two-dimensional. Okay. And let's look at the second statement, right? So let's multiply cosine with sine, right? And now you see when you take the pre-image of 0, you get a union of vertical lines and horizontal lines. Okay, so you will get union of vertical lines and horizontal lines. And the number of these lines are precisely determined by k, right? So you look at these intersections here, right? Then you see that the preimage of 0 is not a smooth hypersurface, right? So in particular, 0 is not a regular value. Any questions about this example?
Very clear.
So sorry. Okay, so we say that a geometric property is generic, right, in this talk, right? A geometric property is generic if it holds on a residual set of metrics, right? Of course, in a certain suitable space of metrics with the topology. Now, it's natural to ask whether a similar result holds for C-infinity metrics. This is a result of Tanikawa, so analogous result holds for a space of C-infinity metrics. And what's interesting here is this type of results do not hold in general for Laplace acting on forms. So if you have an even dimensional manifold and the P is the middle dimension, then the dimension of eigenspaces even. So in particular, the generic irreducibility, generic simplicity here cannot hold. Okay. I should also mention that in this theorem, to get the first statement, you only need L to be greater than or equal to 2. To get the second statement, you need L to be greater than or equal to the dimension of the manifold. Okay, now what's the opposite of a generic metric? To me, the opposite is a metric with symmetries. Okay, so now we will assume that we have a finite group or a compact Lie group acting on a closed Riemannian manifold by isometries. Then we can define a left regular representation of G on C-infinity functions as follows. So given a C-infinity function f, right, I define UH of f to be another function, right, such that UHF of P is f of H inverse acting on P, right, for each element H inside of G. So this is a representation. And because our group acts by isometries, the Laplace operator and the unitary representation, the left regular representation commutes. As a result, if you have a lambda eigenfunction, which means that Laplace of f is equal to lambda times f, then Laplace of UHF, right, is UH Laplace f because these operator commutes. And because f is a lambda eigenfunction, this is UH of lambda f. Okay, and then you can take this out and get lambda times UHF. So what that means is UHF is again an eigenfunction. So in other words, UH sends eigenfunction to eigenfunctions with the same eigenvalue. So we have UH sends E lambda to E lambda. And in particular, E lambda is a representation of the group G. Now, this representation may not be irreducible in general. Okay, so here I will give you two examples. So consider these two cases. So first, we have the group is S1 and M is the round 2 sphere. So now I have a round 2 sphere inside of X, Y, Z axis. Now let's assume that G acts on the sphere by rotation of the Z axis, around the Z axis. So suppose that S1 acts this way. Okay, this action is an isometry. It's an action of isometries. And now let's look at the eigenspaces of S2. Let's just look at the first eigenspace. So E lambda 1 is given by a span of X, Y, and Z restricted on the sphere. So in particular, the dimension of E lambda 1 is equal to 3. But we know that irreducible of representations of S1 are at most two-dimensional. I'll talk about those representations later. So we know that E lambda 1 cannot be an irreducible representation. So E lambda 1 is not an irreducible representation. Now, let's look at another example. Now we have SON plus 1 acting on Sn instead, right? So now we have n sphere. And the eigenspaces are given by spherical harmonics, or they're given by harmonic homogeneous polynomials of the same degree, right? So it is known that now each eigenspace is an irreducible representation of the group G. Okay, so eigenspaces are irreducible representations of G. Okay, so now as you can see, right, this problem really, whether eigenspaces are irreducible, really depends on the group you pick. Now, the following problem / conjecture originated from quantum mechanics and atomic physics. The problem, so today I'll use the problem to say that as a problem. So suppose that G is a compact Lie group or a finite group acting on a manifold M, right? And this problem says we want to show that for a generic G invariant metric on M, of course, in a suitable sense, right? Each real eigenspace is an irreducible G representation. Okay, so if you change that real to like complex or quaternion is not true. Okay, so I'll explain why I associate those four names with the problem in the next slide. Okay, so another way of stating this problem is, okay, we want to show that generically, these eigenspaces are in fact irreducible representations. And this problem / conjecture has something to do with accidental degeneracy. Since I'm not the expert in this area, so I won't go into details about that. Okay, so let's look at some history of the results in this direction. In 1990, Zeldich first proved the case for finite groups. So in his case, G is a finite group with a high dimension, low degree assumption. So Zeldich needs to assume that the dimension of the manifold is greater than the largest degree of the representation of gamma. Now, the full conjecture for finite group is still open. Okay, so what Zeldich showed is that if you, for a generic gamma invariant metric, right, if gamma satisfies this condition, then each eigenspace is an irreducible gamma representation for a generic metric, of course. Now, in this same paper, Zeldich cite Wigner, so Wigner's book, and saying that this is a well-known, right, conjecture from physics. And Zeldich also noted in that same paper that his method wouldn't work for Lie group actions. In 2017, inspired by a question by Victor Gilman, Dorothee Schuth proved that for a generic left invariant metric on SU2 or product of SU2, each eigenspace is an irreducible representation. So in her case, the group G is SU2 or product of SU2, and M is the same as the group G. Now here, another result in 2020, Junhyou and Zeldich proved generic irreducibility for Kaluza-Klein metrics on unit cotangent bundle. Okay, these are very special, somewhat special metrics on the unit cotangent bundle. In particular, G is equal to S1 in their theorem. And these metrics have the special property that each fiber is in fact totally geodesic. Now, I mentioned these three results, but there are some other results in this direction, which I omitted. Now, I mentioned Yao's name because problem 1 is also in Yao's famous list of problems in differential geometry, published in early 1990s. This is specifically problem 42. And I must say I learned this flag from a review by Emilia Lorette. Okay. We solved this case for free torus actions. So let's recall what are the representation or irreducible representations of tori. Any questions about this slide? Okay, so I'll move on to a short review on irreducible representations. So now suppose that we have TD, right, D-dimensional torus. This is a product of S1 as a group, right? So you have D factors. Irreducible representations of tori are parameterized by these integers, right? So for each alpha inside of ZD, we have an irreducible representation of the torus. And this irreducible representation is given by the following. So for each element, theta 1 to theta D inside of torus, right, we send this element to rotation, which is an element inside of GL2R. So this alpha dot theta is the dot product between alpha and theta, and R is the rotation by degree, by angle phi. Okay. So in particular, each irreducible representation is two-dimensional. So what's our theorem? So we solve the problem for the case of free torus action. We already generalized this result to non-free actions as well. So for this theorem, we actually don't need a free assumption, right? So suppose that, and this result will be on archive soon. Okay, so suppose that we have a connected closed manifold of dimension n greater than d, and assume that the dimensional torus acts freely and smoothly on the manifold M. And like before, we let MTL be the space of CL torus invariant metrics on M. Then our theorem says, for each L greater than or equal to the dimension of the manifold, there exists a residual set, RL, inside of MLT, such that for each metric inside of this residual set, if a Laplace eigenfunction is invariant, which means that it's constant along each torus orbit, then it is contained in a one-dimensional eigenspace, the trivial. So that means the eigenspace is a trivial representation. If an eigenfunction is non-invariant, which means that it's non-constant along any torus orbit, then it must be in a two-dimensional eigenspace. So in light of the previous slides, it means that if you have a non-invariant eigenfunction, let's say u, right, from MR to R is non-invariant, right, then you can find its pair, right? So then you can find u2, right? So then you can find, you can let u to be u, and another function u2, such that u1, u2 of theta inverse dot p is equal to r alpha theta u1, u2 of p for some alpha. And the second part is that 0 is a regular value for each eigenfunction. Okay. Now, in 2022, Jung and Zeldovich generalized their result to principal S1 bundles over manifolds of dimension greater than 2. So in their results in 2020, their metrics are defined on unit cotangent bundle of surfaces, but now they can, but in 2022, right, they generalize this to bundles over manifolds of dimension greater than 2. But in our theorem, we specific for this, right, it still works for torus. Okay, so what are some examples where this theorem applies? First, we have a Hopf vibration or Hopf bundle, S1, S2, and plus 1 to CP. Right, so from this theorem, we know that for a generic S1 invariant metric on S2n plus 1, these two properties hold. And another example is two-step new manifolds, and which are manifolds that are covered by two-step nilpotent Lie groups with left invariant metrics. And those manifolds are torus bundles, right, as well. So again, this theorem works, right, for torus invariant metrics. Okay, now I'd like to mention some applications to nodal domains of this result. This is really from the original idea of Jung and Zeldovich in 2020. So let phi be a real eigenfunction. The nodal set of phi is defined as the preimage of 0. And each connected component of M minus a nodal set is called a nodal domain. Now I will let this curly n of phi to denote the number of nodal domain of this eigenfunction phi. Now, if phi is not a constant eigenfunction, then we know that the inner product with the constant is 0. And hence, the number of nodal domains for non-constant eigenfunction is greater than or equal to 2. On the other hand, by Courant's nodal domain theorem, for a kth eigenfunction phi k, the number of nodal domains is at most k plus 1. Now, various asymptotic improvements were obtained in the past, and to get a good idea of those results, I think the last talk last week is nice, summarizes nicely. Okay, so let me mention our applications for nodal domains. Okay, so assume that T, the torus, acts smoothly and freely on M, such that the dimension of the quotient space is greater than or equal to 2. Now, let me mention that in the previous theorem, we don't require the action to be free, but in this theorem, we do require the action to be free. There are some counterexample in the paper by Jung and Zeldovich in 2022. And the second thing I want to highlight is this dimension assumption. So here I need the dimensional quotient space to be greater than or equal to 2, whereas in the previous theorem, I only required this quotient to be at least one dimension. So for a generic T-invariant metric on M, in the sense of theorem 2, right? So there exists a residual set of invariant metric, right, such as this fold. If a non-constant eigenfunction vanishes on some torus orbit, then the preimage of 0 is connected. So nodal set is connected. And since there are at least two nodal domains, so we know that number of nodal domains is equal to 2. In 2020, Zhu and Zeldich proved this for Kaluza-Klein metrics on unit cotangent bundle of surfaces. So our theorem is a generalization of this result. Now, of course, you might ask, how many eigenfunction vanishes on some torus orbit? With a topological assumption, we can ensure that each non-constant eigenfunction vanishes on some S1 orbit. Sorry, I meant non-invariant. Okay, so not just non-constant, but non-invariant. Okay, so this is a corollary of theorem 3. Suppose that you have a connected manifold B such that the second cohomology BZ is torsion-free, and we assume that M is a non-trivial orientable S1 bundle over B. Okay. Then for a generic S1 invariant metric, each non-invariant eigenfunction has precisely 2 nodal domains. Okay, so let me just say a few words about how we get this. So what we did is we realized that, okay, so for a eigenfunction to vanish on some T orbit, right, this is equivalent to some section of some bundle vanishes at some point, right? And section of a bundle vanish, S1 bundle vanish at some point, if and only if some Chern class, well, it's not 0, right? So that gives you some what I call this, some obstruction, right? So that's how we get this condition here. Okay, so how many eigenfunctions are there, right? So I should say, how many non-invariant eigenfunctions are there? There are a lot. Okay, so let me state our corollary in a slightly different way using wild density. So suppose that we have a orthonormal basis of eigenfunctions with the eigenvalue lambda I. So here what we have is phi1, phi2, and phi3, phi4, and so on, right? And suppose that we have a subsequence, okay? So now I pick some part of the sequence, right? So 4, and so on, right? Right, so now let me form the set A. So A is a subset of natural numbers. So for this circle subsequence, right, A is equal to 2, 4, and so on, right? So the wild density of a subsequence phi I belongs to A, is defined as a limit soup 1 over n of lambda, where n is the counting function of a number of eigenvalues satisfying that are inside of A less than lambda. So if A is the whole natural number, then the wild density is equal to 1. Okay, so let's rephrase corollary 5 using wild density. So again, we let B be a connected manifold such that H2 BZ is torsion-free, and let M be a non-trivial oriented S1 bundle over B. Then for a generic S1 invariant metric, every orthonormal basis of eigenfunctions emits wild density 1 subsequence, such that each eigenfunction has only, in the subsequence, has only 2 nodal domains. So the next fact is for those of you who are more interested in quantum chaos. So know that if S1 acts on M isometries, then the geodesic flow cannot be ergodic. So this color ray, in some sense, highlights the importance of ergodicity assumptions in quantum chaos. Okay, since I'm not the expert of this area, I'll leave it as that. Color ray 4 and 6 were also proved independently by Jung and Zeldich in 2022. We published our preprints roughly around the same time. However, Jung and Zeldich's proof is based on a version of theorem 3 for S1 actions, not torus actions. Now, while we both use Uhlenbeck's framework, our implementations are quite different. In Jung and Zeldich 2020, they identify some operator with the Bachmann-Laplacian, which we'll mention again. And here we just deal with the isotypical components directly. I'll mention those terms more carefully later. Okay, for the remaining time, I'd like to give you a strategy for proving generic irreducibility. Okay, so that means I want to give you a strategy of proving that for generic Torus-Invariant metric, each eigenspace is irreducible representation. Okay. So suppose that we have a compact Lie group acting on M, then we have a regular representation on HK of M. This is the Sobolev space HK of M. Right, K is the regularity, right? So we again have this representation of HK, and because G is compact, right, we can decompose our HK of M into a orthogonal sum of irreducible representations. Okay. Now I can first fix a real irreducible representation, okay? And we let IK of V be the isotypical component of V inside of HK for the left regular representation. So what that means is I look at all representations inside of HK that are isomorphic to V and sum them together, right? So I have IK of V is the sum of VM, where VM is a representation that's isomorphic to the representation I fixed in the beginning. So this is called the isotypical component. Next, I define a restriction, right? So I write Laplace V, right, to be the restriction of Laplace operator on the isotypical component inside of HK, right? Then this Laplace operator here sends isotypical component to isotypical component. This is basically due to the fact that you have action by isometries. Okay, so to prove generic irreducibility, right, it suffices to establish the following two. We call the first one generic separability and the second one generic G-simplicity. Okay. What does separability means? It means if you pick two non-isomorphic representations, V and W, then the spectrum of this restricted operator for V is different from the spectrum of the restricted operator for W. So if you establish generic separability, that would mean that each eigenspace will consist of one particular representation, but we don't know how many representations there are, right? So each eigenspace, right, will consist of just one type of representation. So perhaps V, some V, some V, and so on, right? We don't know how many they are, but we know that it consists of just one type of irreducible representation. Next, we want to establish generic G-simplicity, which means that for each eigenvalue in this restricted operator, right, the dimension of each E lambda is precisely dimension of V. So if you establish 2, then you know that E lambda must be just consists of one factor, which is V itself. So from this, these two, right, you can prove that each eigenspace is irreducible. So our approach for 1 and 2, for that establishing 1 and 2, would depend on an abstract component and a concrete component. Okay. So the abstract framework will work for other groups. What's more difficult is the concrete components. More about that later. Okay, so for the first part, the proof uses perturbation theory, very classical perturbation theory. We use this to obtain what we call the Kato basis for eigenfunctions. This is already observed a long time ago. And then we want to use the fact we have these representations, right, to show that we have generic separability. Okay. The second part uses Uhlenbeck's framework, a revised Uhlenbeck's framework. So we'll use parametric transversality theorem in Uhlenbeck's original paper to prove this. So for the remaining part of this talk, I'd like to tell you how we set up this framework for our problem. Okay, so I will skip this one, talk about this one. Okay, so what is the parametric transversality theorem? Suppose that you have two maps between Hilbert manifolds. This is our version, but there are other variations. I don't mean it to be our version, but this is what we use. Okay, we didn't invent this, of course. Okay, so we have a map from X to Y, and then we have a map from X to B. So B is going to be our space of metrics. So you can also think of this space B as your space of parameters. Okay, suppose that these two maps are CL between Hilbert manifolds satisfying 1. This map pi is a submersion. And for each point B in the base, you look at the preimage and inside of X and restrict F on the preimage. Right. We want this to be a Fredholm map such that Fredholm index is less than L. This L is the same as the regularity here, L. Okay. The theorem says if Y is a regular value of F, capital F, then there exists a residual set R inside of B, such that for each B inside of this residual set, Y is a regular value for the restricted map. So that's why it's called the parametric transversality. Okay, now let's see how Uhlenbeck proved the theorem for generic simplicity. Okay, so how did Uhlenbeck apply this theorem to prove generic simplicity? So first, we start with a space of CL Riemannian metric on M with L greater than or equal to 2. Like I said, this theorem works when L is greater than or equal to 2. So now we define capital F to be a map from HK cross R cross the space of metric to HK minus 2 of M, right? So this map is defined as follows. F of U lambda G is Laplace G minus lambda U. Okay. So in the context of previous slide, this is the X in the previous slide. And this is your space B. And the map pi is the natural projection from X to B. And of course, Y is this, right? So we have X to Y and X to B, right? Two CL maps. Okay, so we need to, yeah. So now let's let Fg u lambda be f of u lambda g. So this is like the f restricted on pi inverse of g in the previous slide. Okay. Okay. Then Uhlenbeck's argument is based on a simple observation stated in lemma 8. Suppose that you have an eigenfunction, right, of lambda. Then the dimension of the eigenspace is 1 if and only if 0 is the regular value of Fg, right? So you want to apply a theorem above, right, with y equals 0, right, to prove this. So to prove generic simplicity, you just need to show that the map capital F has 0 as the regular value. And that is where the concrete part comes in, right? So you need some concrete argument, right? Specific understanding of how the operator varies along perturbations, right? Or to show this. Okay. Now, the natural question is, how do we generalize this argument to prove generic G simplicity, right? So after all, this lemma is about showing something is one-dimensional. But what we want is to show that something has dimension 2, right, for torus representations. For other representations, we even want to show that something has dimension v, right? So how do we modify this approach to prove generic G simplicity? Okay, so what we're going to do is to define an operator on vector value functions. Okay. So that's what we're going to do. So now we replace HK by HK alpha. So what's HK alpha? So this alpha is our parameter for the representation. So alpha is some tuple, D tuple. So for each representation, we define HK alpha as follows. So this is a space of vector value functions so that each component is inside of HK. Each component has the right regularity. And for each theta inside of the group, right, it satisfies the following. So theta dot u, which is the left regular representation. Okay, so it's defined as u1 of theta inverse dot p, u2 of theta inverse dot p, right? We want this to be equal to r of alpha dot theta u1 u2. Okay, so set of function like this satisfying 1 is what we call HK alpha. So for each alpha, you have a HK alpha. And then we can define vector value Laplacian. Okay, so Laplace of G alpha is going to be a it's going to be just taking Laplacian of each component. Okay, so because the action commute, because the left regular representation commutes with Laplace operator, we can also show that this vector value Laplacian sends HK alpha to k minus 2 alpha. Now, if u is eigenfunction, then u star, let's define u star to be minus u2 u1, right? This is also in here. Furthermore, their dot products are 0. Okay. So from this, we know that the kernel of this vector value Laplacian is at least 2-dimensional. So then I'm going to define a map that's going to give us the corresponding result. So let F be a map from HK alpha cross R2 cross MT, right, to hk minus 1, hk minus 2 alpha, right? So we define this as f of u a b g equals a plus g alpha u minus au minus bu star. Note that each component here is, each function here, right, has 2 components. Okay. Now you might say that, okay, it's starting to look like you're doing something about complex eigenfunctions. Why do you like do this kind of silly thing, right? The reason is because this space MT is really a real vector space. It's not a complex vector space. Of course, you can complexify it, but for things to work nicely, we want to convert everything to real instead of doing this for complex. Okay, so now we have this map, right? And like before, we define FGUAB to be f of UABG. Okay. So know that f of UABG is equal to 0 if and only if u plus u1 plus iu2 is a complex eigenfunction with eigenvalue a plus bi. Because eigenvalues of Laplacian are real, so that means b must be 0. So we have this specific form of preimage of 0 for each metric here. Okay, so now our key observation is the following. Suppose that u is non-zero eigenfunction, right? This is what this means. With eigenvalue lambda, then the eigenspace of this vector value Laplacian is exactly 2-dimensional if and only if dfg u lambda 0 is surjective. So now we can apply parametric, we want to apply parametric transversality theorem to prove that 0 is a regular value for fg generically, right? And I should say that this framework also works for other representations. So for groups that are not tori, right? So what you would do is you would look at the type of representation. So you will have real type, complex type, and quaternionic type. So for real type, you would just have A right here, right? You wouldn't have this weird BU star. For quaternionic type, you will have 2 additional factors. But the main obstacles is now the concrete part of the arguments. So for other representations, it's difficult to see whether that concrete part of argument will work, right? Okay. So, and this is what we are studying right now. And I also want to mention that we also try to, we are also generalizing this to other boundary conditions or other eigenvalue problems. Thank you for your attention, and this is all I want to say.
Thanks a lot, Sam, for this talk. We now have time for some questions. So if you have questions, either unmute yourself or write them in chat.
Okay, I have some questions. Thank you for the interesting talk. Have you tried to generalize this to the general compact Lie groups? And if yes, then what is the difficulties?
Yeah, so we tried, but we haven't succeeded. Okay, so the thing is, for the Uhlenbecks, we kind of face a similar problem like the one in Zelda's result 1990. So when you apply Uhlenbeck's framework, now you reduce this to a linear algebra. Eventually, you reduce this to a linear algebra problem. And unfortunately, as the dimension of the representation increase, right, degree of representation increase, you get more and more variable for this linear algebra problem. It's more and more difficult to use finite amount dimension of like perturbations to solve this problem. So perhaps it's maybe it's hopeful, right? We can restrict the dimension of representation to be less than the dimension of manifold. Maybe there is something to be said there. Yeah.
Okay. Okay. Thank you. Another question. So you mentioned non-free actions, and the question is how we use free that the action is free in this reasoning. Where is it an essential point? Really?
Yeah. So originally we thought we can only do this free actions because we don't understand our perturbation formula enough. So it is possible to fully utilize this perturbation argument and then do things pointwise instead of like I don't know how to describe it, instead of doing this this weaker version of this argument. Yes, it's difficult to say, but when we fully understand our action and then fully understand how groups act, right? So originally we look at surface revolution and thought there's our argument wouldn't work for it. But then when we look at surface revolution closer, then we understand how things work. So this argument we're going to have for non-free action will be like, we'll have like two parts. One is where dimension is greater than 3, and the other is two-dimensional case.
You,
Okay,
Igor,
thank
for
you.
the question. Do we have other questions for the speaker? Right. Well, let's thank Sam again for this very nice talk and very instructive talk on the methods that he used and of and on this general Uhlenbeck framework. So thanks again, Sam, and we will reconvene next week at the same time.
With the talk by Dan Mangubi, actually.
Yes, exactly.
The
Yeah.
recherches of nodal domains.
Thanks, Alexandre, and thank you. Thanks a lot.
Thank you.
Thanks a lot, Sam, for this talk.
Thank you
Sam.
for